So in two other videos, we looked at bulk composition A and this white dot over here to find out how those would evolve. What if we had a liquid composition sitting here? What would happen with this fellow? Well, we'll take a look at it relative to this dashed line. We must end up with a rock that falls within this region where we get anorthite plus a silica-rich phase. Well, not just silica-rich, but pure silica. It'll be a mixture of anorthite plus tridymite and enstatite. There will be no olivine. This fellow here is in this enstatite plus liquid field, so it's never going to create the forsterite that we had with point A or the white dot that we showed over here. We would draw a line emanating from enstatite, not this 1557 point there. That's where the peritectic intersects this forsterite plus SiO2 line. So we're going to have a line that emanates directly from enstatite that'll go through that white point and hit this anorthite plus enstatite cotectic here. And as it begins crystallizing anorthite, the liquid will migrate down to this ternary eutectic here at 1220 degrees, where it will crystallize out tridymite and anorthite and enstatite will crystallize together until the rock is completely crystalline. Now we could take this fellow here and drag it to, let's say, this point over here, and would have a similar kind of system. So notice the way we had it here is just a simple ternary eutectic. We're avoiding this peritectic altogether, so we don't have that crazy stuff that was going on in the previous diagram. And the same is going to be true for a lot of the compositions that plot in this field. If we had something that fell in this position here, we would move directly away from silica, and it looks like we'd precipitate out cristobalite first. And as we precipitate out cristobalite, the melt would migrate and hit this curve here. Then it would enstatite would join the team. Enstatite and cristobalite would, cristobalite will convert to tridymite. Enstatite and tridymite will crystallize together until we hit 1220, and that's when anorthite will join the club and they'll precipitate out together until we have the last little bit of liquid disappearing. The temperature would remain constant at 1220 until the last little bit of liquid is crystallized, and then we'd have a rock that would be in this position here. It's still made of anorthite plus silica-rich polymorph and enstatite, but just in different proportions. With a little more quartz-rich polymorph than we would have over here. Same thing happens more or less, just minus a few details if we had a composition over here. So let's say we had this white dot over here. We're starting in the anorthite plus liquid field, would crystallize pure anorthite. The liquid would move away from that anorthite apex until it's saturated with cristobalite. Then the liquid would be saturated with both anorthite and cristobalite. That cristobalite here would convert to tridymite as it crosses that dashed boundary. And then by the time we get here, that's when enstatite would join the club. And again, just like in the ternary eutectic system, we would have a rock, we would have a liquid that would precipitate out all three minerals at constant temperature until all of the liquid is gone. Now, what happens if we had a liquid that was way over here? Well, that's where this part of the diagram is being simplified. We would crystallize anorthite. We might actually be crystallizing spinel. There's this little triangular spinel field here that's being simplified. If we did not, let's just say we ignore spinel, then we would crystallize anorthite first, but now it would be like the other systems that we've shown. Notice that this white dot is now on the left side of this dashed curve. So that means our final rock has to be a mixture of anorthite plus enstatite plus forsterite. We would crystallize anorthite until we would hit the forsterite plus liquid field here, and we would follow that pseudo-cotectic, really, because spinel does come into play here, and would crystallize anorthite and forsterite together until we reach 1270 degrees, and then at 1270 the liquid would begin to react with forsterite to create enstatite, and then the three minerals will appear together. Well, not really precipitating together. There is this reaction relationship. Forsterite is going to decrease in abundance, but in this case, liquid will be our limiting reagent, and we will not have enough melt to react out all of the forsterite. There will be some forsterite left over, and we'll end up with a rock that's forsterite plus anorthite plus the enstatite that's created at that reaction at 1270 here. 1270 would be the lowest temperature that that liquid would see. And then just for one final example, let's see if we can move this fellow without resizing it. So we can, well, maybe we just have to make it very large. And now we can move it. So let's say we had a bulk composition here, would move directly away from anorthite, and we would hit the enstatite plus anorthite eutectic. Now the peritectic is totally irrelevant. We never had forsterite to begin with, and we're on the right-hand side of that dashed curve. And as we move away from anorthite and make enstatite, would move down temperature, hit the ternary eutectic, and we would crystallize out tridymite at 1220 degrees, and that would be our final assemblage. So that wraps up our discussion of this rather odd but still rather important ternary of anorthite, forsterite, and silica polymorphs.